We, humans, operate as Bayesians who build on our existing knowledge. What we know as of now, it's updated when we receive more information or data. In this video, we will introduce the Bayesian knowledge building process using an example. And as we go through the example, I will introduce key concepts and terminologies in Bayesian statistical analysis, all right? You may have heard of the popular word puzzle game called Wordle. How can we use a Bayesian knowledge building paradigm to solve Wordle? By the way, I'm using the version from the New York Times. Point of the Wordle game is to correctly guess a hidden word in six or less guesses. After each guess, you get clues, and the color of the tiles tells you how close your guess is to the hidden word. As you can see in the instruction, W, which is in green, is in the hidden word, and it is in the correct spot. The yellow like color tells you the letter is in the hidden word, but it is not in the right spot. The dark gray color tells you that the letter is not in the hidden word or it's not in the Wordle. So let me play one game to make the instructions really concrete. My first guess is arise. I played arise since it has vowels which tend to occur more often in five-letter words. It also has letters such as S and R, which tend to occur often as well. And I get a clue after I play the word. The clue tells me that the letters A, R, and S are not part of the hidden word, but the letters I and E are in the hidden word, but not in the spots I put them on. So I use this additional information to update my belief of what the wordle or what the hidden word is. My second guess is FIELD, field. Now the letter E is in the correct spot. I also get information that the letters F, L, and E are not in the hidden word. With this, I again update my belief of what the secret, what the hidden word is. Let me try PIETY. I get more information to update my belief about the secret word. Finally, I try INEPT, and it turns out that's the correct word. All the tiles are green, and I get the secret word, or I get the wordle correctly guessed, and four tries, four trials. Okay, now that you have an idea of how the game is played, let's play another round of the game. This time, I will introduce key terminologies and Bayesian knowledge building paradigm more concretely. At the start of the game, when you have a blank slate, essentially, you are best served if your guess includes letters that occur more often, such as vowels, or letters such as S and R and T that occur more frequently. Higher the weight assigned to a letter, the more you want that letter to be included in your next guess. So prior to playing any round, what is your prior weight? What are your prior weights that you assign to these letters? So I'm using a keyword prior here. So prior to getting any data or any information about the hidden word, how much weight do you place on whether a letter is one of the characters in the hidden word? Okay. In this particular example, prior is what letters I believe will be present in the hidden word before observing any clue. In other words, our prior governs which letters we choose to make the initial Wordle guess. As a general Bayesian term, prior is a belief about a scenario we want to model before observing any data. It is a belief, it's our belief about parameters we seek to estimate before seeing any data. All right. So in this example, our prior weights are based on favoring vowels and favoring consonants like R, T, L, S, which occur more often in five-letter words. So I am likely to guess words such as atone, bears, cater, crate, rate, store, or even trace based on my prior weights. I'm going to go with bears. It may not be the most optimal one. That's really not the point of the lesson. The lesson is about knowledge building process the Bayesian way. Our initial guess reveals clues. Now we know B, A, R, and S are not in the hidden word. I also know that the letter E is in the word that I'm looking for. It is also in the correct spot. This is new observed. This is new evidence. That's another word you might hear. Armed with this data or with this evidence, you can update your prior. Now you know the letters B, A, R, and S, which in your initial prior were given very high weights, will have an updated posterior weight of 0. Posterior is another key Bayesian terminology here. So these letters, which are in black, B, A, R, and S, will have a posterior weight of 0. When you update your prior information based on observed data, it becomes your posterior information. You combine your prior with newly observed data to have an updated posterior information about the problem at hand. You are accumulating knowledge. This is how humans operate. We don't completely forget our past. We build on it. Our prior experiences guide us in making decisions and taking actions. We observe data as a result of our actions. This new insight from observed data is then combined with our prior experience to give us an updated knowledge about what we want to solve for. That updated knowledge is called the posterior. All right. Post data. Prior is pre before observing data. So Bayesian approach gives us a formal way to accumulate knowledge or to update our beliefs based on observed data. So going back to the example, the updated weights about which letters are in the hidden word now place higher emphasis on letters such as E, O, N, L, and T. With this updated information, maybe hotel or inlet, outed, tenant, or tweet or voted could be good guesses. Let's try one of them. OUTED, outed. Oh, wow. Even though we did not have an additional letter other than E confirmed as part of the hidden word, we now have better information about Wordle or the hidden word. Knowing letters O, U, T, and D not being part of the Wordle is an additional piece of information to really gain further knowledge about the hidden word. So, for example, initially, our top suggested letters were E, A, R, O, and T. We then updated them based on observed data, and we dropped some letters from the top suggestions, and then we had E, O, N, L, and T. More data or evidence now allows us to make further update. And our top suggested letters are E, L, N, I, and X. Here's a bar graph showing our updated posterior, giving more weight to some letters than it did before, and some less. We are building on our knowledge of what that hidden word is. Perhaps here are some words from our updated posterior that are good guesses. GIVEN or HINEN, lichen, LIKEN, or pixel are good words for instance. Let's go with given. All right. We play that and we get more data. The letter I is in the secret word and it is in the second spot. We now know that the letter N is in the hidden word, but not in the fifth spot. So I need to move it. What else? I also know that G and V are not in the hidden word. You get the idea. We have our belief, we get data, we update it. We get more data, we update our belief. So I'm going to move quickly here. All right. Our top suggested letters are now E, N, E, Y, N, W, P, and Y. So let's go ahead with W, I, N, E, Y. Almost there. Almost there. How about P, I, N, E, Y? That is the hidden word we're looking for. Okay. The purpose of this video is really to give you a big picture view of Bayesian paradigm of knowledge building in which we update our prior belief as we observe more data or evidence. The updated information is called posterior information. Posterior is something we get by combining our prior with observed data. So Bayesian approach gives us a principled way of combining our prior beliefs with observed data to get an updated posterior. My hope is that this lesson is also a data point, an observed data you take to update your knowledge about how you do statistical analysis. All right? I want to give a shout out to a book whose first chapter really inspired this lesson. That book is Bayes' Rules, an introduction to applied Bayesian modeling.